In chemistry, a glycosidic bond is a type of covalent bond that joins a carbohydrate molecule to another group, which may or may not be another carbohydrate. A glycosidic bond is formed between the hemiacetal or hemiketal group of a saccharide and the hydroxyl group of some compound such as an alcohol. A substance containing a glycosidic bond is a glycoside. The term glycoside is now extended to also cover compounds with bonds formed between hemiacetal groups of sugars and several chemical groups other than hydroxyls, such as SR, CR, NR1 or 2, or even CR1 or 2 or 3. Particularly in naturally occurring glycosides, the compound row from which the carbohydrate residue has been removed is often termed the aglycon, and the carbohydrate residue itself is sometimes referred to as the glycon. S, N, C, and O glycosidic bonds. Glycosidic bonds of the form discussed above are known as O-glycosidic bonds, in reference to the glycosidic oxygen that links the glycoside to the aglycon or reducing N-sugar. In analogy, one also considers S-glycosidic bonds, where the oxygen of the glycosidic bond is replaced with a sulfur atom. In the same way, N-glycosidic bonds have the glycosidic bond oxygen replaced with nitrogen. Substances containing N-glycosidic bonds are also known as glycosilamines. The term N-glycoside is considered a misnomer by IUPAC and is discouraged. C-glycosyl bonds have the glycosidic oxygen replaced by a carbon. All of these modified glycosidic bonds have different susceptibility to hydrolysis, and in the case of C-glycosyl structures, they are typically more resistant to hydrolyses. Numbering, and I plus or minus / I squared distinction of glycosidic bonds. One distinguishes between I plus or minus and I squared glycosidic bonds based on the relative stereochemistry of the anomeric position and the stereocenter furthest from C1 in the saccharide. An I plus or minus glycosidic bond is formed when both carbons have the same stereochemistry, whereas a I squared glycosidic bond occurs when the two carbons have different stereochemistry. One complicating issue is that the alpha and beta conformations were originally defined based on the relative orientation of the major constituents in a Haworth projection. In this case, for D sugars, a beta conformation would see the major constituent at each carbon drawn above the plane of the ring, while alpha would see the anomeric constituent below the ring. For L sugars, the definitions would then, necessarily, reverse. This is worth noting as these older definitions still permeate the literature and can lead to confusion. Pharmacologists often join substances to glucuronic acid via glycosidic bonds in order to increase their water solubility. This is known as glucuronidation. Many other glycosides have important physiological functions. Glycoside hydrolases are enzymes that break glycosidic bonds. Glycoside hydrolases typically can act either on I plus or minus or on I squared glycosidic bonds, but not on both. Glycosyl transferases, before monosaccharide units are incorporated into glycoproteins, polysaccharides, or lipids in living organisms, they are typically first activated by being joined via a glycosidic bond to the phosphate group of a nucleotide such as uridine diphosphate, guanosine diphosphate, thymidine diphosphate, or cytidine monophosphate. These activated biochemical intermediates are known as sugar nucleotides or sugar donors. Many biosynthetic pathways use mono or oligosaccharides activated by a diphosphate linkage to lipids, such as doligol. These activated donors are then substrates for enzymes known as glycosyl transferases, which transfer the sugar unit from the activated donor to an accepting nucleophile. References. External links, definition of glycosides, from the IUPAC Compendium of Chemical Terminology, The Gold Book, Varkey al. Essentials of Glycobiology. Cold Spring Harbor Laboratory Press. 1999. Searchable online.